Sure. Yeah, thanks everyone for attending, and it's a pleasure to present our work, Uncertainty and Understanding of the LLM explanations from the reasoning topology perspective. So before we get started, I'd like to ask the question, like, can we actually trust the LLMs? Yeah, so I believe everybody uses it, and maybe it has become a habit to use it to solve some of the like trivial tasks in the daily lives. But like, why is trivial tasks is I believe everybody has an answer. Like sometimes it hallucinates, and yet we do not quite know how to deal with it yet. And this is an example. Like you ask a question, and it just makes a fake answer. And then if you don't know the answer and you want to rely on it to give an answer, then you don't know if it's correct or not. Similarly, and it's funny because every single like prevalent language model platforms like ChatGPT or Cloud AI, they all put this sentence here. Like ChatGPT can make mistakes. Be careful and check the information by yourself. Yeah. So and then how do we actually know like language models are reliable or not? We need to understand the uncertainty of these generations. And this slide shows like the current survey of different types of solutions. Mainly, we can categorize them into two directions. One is white box, and another one is black box. White box treats the language model as a white box, and we have access to the token or parameter level and generated probabilities, and it's easier for us to actually precise and understand the uncertainty from a probability way. More people are trying to solve it in a black box way, because we don't know if there are more and more commercial language models, but we do need to understand how they are performing. So we need to understand, even it's black box, it's commercial, we want to get awareness of the uncertainty of their responses. So for the for black box and white box, the very common way to do it is they focus on the multi-round answering. So we can see that given the question and you want to ask it multiple times, and by asking the multiple times, you can actually extract the semantic variance from the multiple responses. Either you embed in the semantic space, or you extract it and to do the agglomerated composition. But there are different ways to do it. But most of them are asking it by multi-rounds and extract the semantic variance. But actually, can this suffice our purpose? Actually, the existing UQ methods, the Q stands for the uncertainty quantification. They have several failure cases and drawbacks. So the first one is they cannot capture the uncertainty in the reasoning process. So as I was mentioning before, so you ask questions and then you expect multiple answers here. But how do you know the reasoning process if the answers are sharing the same meaning? So for example, in here, if you ask if it's summer in Australia or season in Canada, it can answer you multiple times in winter in Canada, winter, repeat it again. And these are all correct, yeah. But how do you know the reasoning process? So this reasoning process is what I elicited by asking the detailed reasoning steps and how you think from different language models. We can see that there are different reasoning topologies that is supporting their responses, and this can generalize to different and more complicated tasks questions. And what if the two answers share the same meaning, but comes from two different reasoning paths? And if that's correct, if the reasoning paths are correct, that's fine. But what if the factual errors actually even exist in the reasoning paths, but they provide consistent answers anyways? Because we know that language models sometimes they memorize the answers because they've seen it in the training corpus. But this will be very difficult tasks. And in order to resolve the current drawbacks, we need to answer the following questions. One is, if we want to understand the reasoning process and get uncertainty from the reasoning process, how can we derive the reasoning contents? And another one is how do we present reasoning structures to support us understanding which step actually made mistakes. So for the reasoning content, we can derive the reasoning information and reasoning steps by switching the target from focusing on the answers to focusing on the explanations. So here, for example, we can use language model explanations, and we pass into the question, and also we pass into the explanation prompts, and ask it not only generate answers but also generates the answers explanations. So this is simple way to do it, but another hard way is how do we represent reasoning structure. Existing work try to adopt the reasoning chain for the uncertainty quantification methods of how different responses are reasoning in the process. But in complex reasoning, single reasoning chain has limited representations of the reasoning characteristics. For example, here we actually show the heat map of the contradictory probability from 10 responses pairwise. And we can see that even the red area here is only 0.14. So it's very low probability of contradictory, even though they actually come from different reasoning structures. And also they actually differ in the major steps. So these, if you try to embed them into the a long reasoning chain, that actually the length of the chain actually limits the representation ability. And in this work, we actually propose to represent the reasoning process naturally as a directed graph. So it starts from the question and how to actually go to the next sub-question, to answer the sub-question and summarize it, and to actually get the conclusion to the final step. And it has several advantages, like comprehensive illustration of the complex reasoning process, structural information for statistic uncertainty analysis, and also can interpret it from which step is problematic. Yeah. Here's the overview of how we extract the graph reasoning topology. So we start with the question, and we expecting answer, and it also comes along with 3 steps reasoning elicitation. So firstly, it reflects what sub-questions and what sub-question is required to solve this question, and then it itself answers the sub-questions. And then for the sub-question and answer pairs, they try to connect between the sub-question pair 1 and pair 2, and actually connect these to form the final reasoning process from the XQ to the actual answer, and how they actually conclude and merge the different answers and responses. And here is the example from node raw. We call node raw as to represent the actual raw question. So we ask the same question: if current summer in Australia was season in Canada, and the edge here made me ask, where is Canada located on Earth? The edge and the nodes, we can think about edge and sub-questions to elicit the node, sub-node. Sub-node is sub-answer. And the sub-question here: where is Australia located? Where is Canada located? What is the geographic relationship between Australia and Canada? And how does tilt of Earth affect seasons? And the answer is step by step. Australia in the southern hemisphere, while Canada is in the northern, and we are in the opposite hemisphere. And opposite hemisphere experience opposite seasons because of the Earth tilt. And actually, we connect these two, and then we combine this here. So we know that edge 0 is asking about Canada. Edge 1 is asking about the Australia, and then when we draw a conclusion, okay, in the middle they are actually opposites. Okay, if the opposites, what's the change? What's the difference? They suffer difference of the seasons. Yeah, and then it comes to the results. And this way can be applicable to a lot of different questions and reasoning process. And these are just some cases to show that also similar questions for some geographic information. Yeah. And then given the different topologies we extracted, how do we actually get the uncertainty from that? So, and here we can actually do a lot of things. In this work, we propose to understand the uncertainty from the reasoning graph edit distance. Because for the first step, we extracted like reasoning topology as a graph, and we can actually understand the graph from like both semantic and the structural differences by the graph edit distance. And here we actually have three main steps. The first step is the semantic embedding. So in order not to lose the semantic information, so we can embed the edge and node we extract just now for the sub questions into the semantic embedding space. And after that, we can just do the reasoning distance from the topology semantics by defining two kind of cost functions. One is a substitution, and another one is deletion or insertion. We can imagine that we want to combine. So we have a lot of different graphs, and we want to actually think about a way that we can move this graph to another one, which is like we have two persons, we have different ways to solve that question. We want to align, okay, which step I'm different from you, and if I change this step to yours, and then that will be aligned. So this cost is actually doing something like that. And after designing such kind of cost by insertion or deletion of different operations to the fine-grained level of the reasoning step by step, we can actually try to find the minimum cost to match the two reasoning responses structures. And then we can extract the GED matrix, and we can use the variance of the GED matrix as the representation of the uncertainty. And that's how we solve the uncertainty problem. And during the process, we also find that we could easily we could find that sorry, this is a little bit blurry, but from node raw to the actual node results, we saw some of the node that actually not used in the final like derivation of the response, like conclusion. So we can so we further did another analysis on the topology-based redundancy quantification. So basically, we try to find the valid paths from the node raw, which is the question, to the final answer. And for those branches and sub nodes that actually not contributing to the final answer, we take as the redundant nodes. We can easily calculate the redundancy rate of the reasoning process. And here we propose three different research questions to illustrate our findings. First one is kind of like topology UQ, actually reveal the uncertainty of our large number model reasoning. So yeah, we conduct the experiment comparison with some existing work. Some work I did in the COTA. Yeah, COTA is basically what I mentioned, like they are using a channel of thoughts, channel of agreement thoughts. Yeah. From different channel of thoughts like chains, and they want to compare whether they have share some differences in the chains. And also we compare with some embedding UQ and entailment UQ across different models on different data sets. We find better correlation between our models, our method response. And what's more, I think it's interesting for this slide, because we find that in the redundancy measure, the GPT-4 mini actually shows a very significantly highly redundancy rate. And this might tell us that the high accuracy comes from a broader search tree space, or they are actually generating a lot of lengths when conducting the reasoning, but they eventually got the final correct step. And another one is comparatively the DeepSeek is relatively low, and this may reveal that the model might be trained on a more flexible way for valid reasoning qualities. And the final finding is that from the proposed topology reasoning elicitation, two LLMs share certain patterns commonly. So we find three patterns after we do the clustering. And the first pattern is actually the model is not reasoning at all. So because from node raw and node result, from node raw to node results, the subnode they are asking is actually a verification of their already existing answer. So it reveals that they already know the answer. Just try to verify. Okay, given the feature asked for the answer, this is the original question, and the middle step is directly ask if object A has such feature. So they assume they already know object A and try to verify that, and then they verify it in job conclusion. This is not actually doing reasoning. And the second pattern is they are doing the forward reasoning like the human beings. So when we ask the question, about like given a feature, ask or answer, and the middle step they try to recall the relevant knowledge, concept, narrow down, and then confirm. So this is how we actually human beings are reasoning naturally. And another one is like combination and verify, a combination of the first two. They try to recall the concept, and on another branch they have seen this before, and they try to verify, and then they find the common information, and then they try to get an answer from that. Yeah. So here are the final slides. Some quickly takeaways. Like reasoning certainty is critical problem for like reveals more trustworthy characteristics, and the graph topology together with the graph distance measure can reflect reasoning uncertainty. And the quality of the existing graphs matter in the graph-based reasoning EQ. And another one is the graph topology also provides a way to quantify the reasoning redundancy by finding the valid paths. Yeah, so if you have interest in the details of the work, please scan the QR code and see the paper and the slides. Thank you.
Okay, so this seems like it's a post hoc reasoning method. Like you have your input, your answer, kind of trying to generate the graph that represents the reasoning. So how do you know that that generated graph is actually faithful to the actual reasoning process? Because the model is not necessarily using that graph when it actually generates its answer.
Oh yeah, so it's not very accurate to say the post hoc because the generating process is actually together with the answering process, so it's together with that. But that's true that's true that focusing on the correctness is not fair because it can be affected by the prompt that we made when they are actually answering the questions. So in this paper, in the comparison part, as in showing this figure, the comparison here, we actually showing the ground truth compared to the ground truth faithfulness rather than accuracy. So like the uncertainty with the correlation with the faithfulness. Yeah, the faithfulness is actually done by the early stopping answering, like by, for example, you have 10 steps, you ask for original question for the answer, you give it another extra step for the answer and another 2 extra steps for the answer, and we actually calculate the faithfulness for each step of these steps. Okay. All right. Thank you.
Thank you.